Welcome everybody to today's technical training webinar. The topic area today is generator rotor windings and specifically the interturn faults. Myself, I am Stephen Densley, the International Business Development Leader for Quartzelec, and the presenter for this session will be Wojciech Betlich, who has a wealth of experience in the design and fault finding in turbogenerator rotors. Wojciech is currently working in the engineering team at Quartzelec. I shall hand over to Wojciech shortly, but just to make you aware that during this presentation, you will be able to ask questions to us by typing them into the Q&A section that you should be able to see in the presentation window. Also, we will be conducting several online polls during this presentation to ask some questions of you to help you understand the presentations, but also to help us improve our webinars for future. So look out for those polls. So without further ado, I shall hand over to Wojciech for today's technical training presentation.
All right, thank you, Steve. Good afternoon, everyone, or good morning to some of you. Indeed, we're going to talk about generator rotor interturn faults today, and I hope that by the end of today you're going to know a lot more about interturn faults. So how many of you are aware of the interturn faults on your machines? I guess not that many, although I don't see you. But we know from experience that thousands of generator rotors are currently running with the interturn fault present, and some technical papers would suggest that up to 50% of your generators might have interturn faults. It's quite a lot when you count all the generators around the world. Having that in mind, you might want to know if all interturn faults are critical, because having that large number of faults, it's something extraordinary. Returning rings already removed and end winding exposed. And what you see here is that interturn insulation sitting in between two adjacent copper turns. And what we need to really remember here is that interturn insulation is very thin. It's usually around 0.5 of the millimeter. That means that it's prone to damage, especially mechanical damage. You're going to find this insulation in every slot, but also you're going to find this insulation in the end winding section. And depending on where you find that interturn fault, you can then take and estimate how critical this fault is for you. So just a few examples, just for you to show what the interturn fault looks like. So it's nothing more than a breakdown in that very thin insulation. So you have those two pictures showing the breakdown. But in here, you can already see a darkening copper, which is the result of the heat going on between two adjacent turns. And that's kind of interesting, because when you think about it, the drop voltage across two adjacent turns is just a few volts, maybe 5. So how come the difference of 5 volts can cause that heat? Well, let me show you another example. So here you see on the left-hand side on the top, you can see already burnt out interturn insulation. And on those two pictures, when you look at the copper condition, you can see copper being molten away. So that's quite critical. Another good example, one of my favorite ones, is the interturn fault that appeared on the top turns in the overhang. So you can see the dark patch sitting here. And you might ask, what's the difference between the interturn fault here or somewhere down below in the coil stack? Well, have a look at this one. So this is the consequence of the interturn fault present in the top turns. The picture here shows the retaining ring insulation, because we need to remember that on top of the overhang you will have retaining rings, which is separated by retaining ring insulation. And in here you can see a hole burned through the retaining ring insulation, causing an air fault. So, would you agree with me that if the interturn fault is on the top turn, is more critical than an interturn fault sitting here on the bottom? I would say yes, because it's much closer to the earth potential and much closer to cause a problem and then consequently the air fault. Now I think this is the most important part of the presentation for you, because we're going to talk about causes of the interturn faults. So something, if you understand, will help you to prevent that from happening. So we're going to go through the bearing gear, then influence of the temperature, frequent load changes, contamination, poor quality during rotor rewind. Yes, we are all human beings, so everybody can make mistakes, even the best ones. And then at the end we're going to mention operation at above the rated parameters. And please notice that in that list I underlined bearing gear. And because it's our experience and our view that the bearing gear is the most common cause of the interturn fault. For those who don't know what the bearing gear is, it's nothing more than the slow speed turning gear where you put your generator when it's at standstill and you don't want your generator rotor to go banana shape, so you keep turning it. Now have a look at this little movie here. So what you see is the coil stack. Well, this is the cross section of one of the slots. It's a 660 megawatt rotor. The speed that the coil stack is turning is 42 RPM, which is very close to what you have in your power station as a bearing gear speed. And you can clearly see the movement of the copper stack. Yeah, can you see it here? That means that it's very easy to damage mechanically your interturn insulation, which is sitting in between copper turns. But also, this movement can cause copper dusting. And as we all know, copper is very conductive. Therefore, you might end up with the conductive debris in the slot section causing further problems. That's why, and let me emphasize that here, bearing gear could be a killer, and it often is. Alright, there's a few minutes of this movie. Let me stop that and let's continue with the presentation, but I think you've seen enough. Alright? Now, temperature and thermal degradation. Let me read that sentence for you. 50% insulation lifetime reduction for each 10 degrees temperature increase. That's an important sentence, I would say, because if you assume that all modern generators have class F insulation, which is 155 centigrades, if the machine is running at that temperature, close to 155, the lifetime is around 3 years. And then the insulation becomes brittle. What we also know, based on that red sentence, is that if the temperature is 30 degrees lower, then we can extend the lifetime of the insulation by around 25 to 30 years. And now think about it. When you buy yourself a new generator and you go to the generator producer, they will tell you that the lifetime of the insulation or the lifespan of that generator will be around 25 to 30 years. Would you agree with me? And I'm going to show you why is that. This is what the designers do. They will put class F insulation system into the rotor, and yet they will design the rotor winding so it doesn't run with the temperature higher than 130 degrees, which is the class B. And thanks to that, we can buy that extra 25 to 30 years. So it's something you don't really have influence over, but we as design engineers, we can actually do it for you. Now, again, very important subject, load cycling and number of started stops. So we all know that load change is nothing more than the consequence of the load change is the current change. And with square of current, you have temperature change. And if you would like to take your pencil and write this down, because it's a rather important equation, and we can calculate thermal expansion of different materials. You don't have to do it now. I've done it for you in Excel, but these are two results. So the left-hand side, let's assume that the length of the copper is 4 meters, the temperature change is 100 degrees, and the delta length, what it means that this is the change of copper length calculated, is 7 millimeters. If you do the same calculation for steel, you're going to end up with around 5 millimeters. So you can see that 2 millimeters difference between two different materials. Now imagine that every time you stop the machine, it goes down to the ambient temperature, say 20, 30 degrees. Then every time you start up the machine, everything heats up by another 100 degrees and everything expands. And you have that cycle, expansion, contraction, and with time, these materials, due to the different thermal coefficient, will get damaged. So this is again one of the main causes of interturn problems. Contamination. So, well, Quartzelect being a service provider, we see a lot of different machines with a lot of different problems, and some of them can be very dirty. So what you see here is rotors, very contaminated rotors with conductive contamination. So this is a mix of oil and carbon dust. And because of that mixture, in these two examples, you can see that the two adjacent coils were bridged. Therefore, you have not only an interturn fault in the coil stack, but you have a fault and short circuit between two adjacent coils. That produces a lot of heat, and these two examples show you the consequence of the rotor having an air fault. So it could be that painful. For you to remember, if you have an air-cooled machines, then these are very prone to that contamination, unlike, say, hydrogen-cooled machines. So air-cooled machines, guys, remember, replace these air filters because it's very, very important. Rewind quality. Wow, I like this example. So the story goes, the machine was rewound, so everything is new, and the customer at the time had an online monitoring system installed. It's called Flux Probe, so they can detect interturn faults. So the machine went back into service, and the operator noticed, hey, we have a problem here. Obviously, they got back to the company that performed that rewind and said that something isn't right. Obviously, the machine was under warranty. They brought it back to the factory, took the return wings off, and they realized, indeed, there is a fault, so they found it. And this is a palm of the hand, and you can see that tiny little debris. We knew afterwards when we analyzed what that debris is, that this is an alloy that we use to brace two copper joints together. And that little alloy broke through the Nomex insulation, causing that interturn fault. So it's a good thing that this particular customer had that online system installed. If he didn't have it, well, most likely he would be running this machine with the fault present, and God knows what would have happened with time. So he was lucky this time. Now, operation above rated parameters. So this is capacity diagram for your generator. And if you focus on that line between A and B, it's red now. This is the limit of the temperature for your rotor. So if for some reason you decide to go over that limit, you have to remember that the temperature of your rotor winding will increase above the design value. Therefore, your insulation will degrade a lot faster. And we've seen that red sentence, you can come back to that later. So yes, don't do it if you can't. I know that many of operators won't exceed that value, but I've seen this happening. Just be careful when you do that and be aware of the consequences. Now, have you ever heard about the relationship between interturn fault and the vibration? Well, if you did, then you're right, because there is a relationship. And let's go through that, huh? Shall we? So, if you have one of the coils with interturn fault present, then that coil will produce less ampere turns. That's obvious, we know that. Then your AVR system or your control system will require higher excitation current to push and obtain the same flux. As a consequence, you're going to end up with a thermal imbalance because one pole with shorter turns will see the hot spots where the other one will be cooler. So you have that banana shape going on, and then you will end up with the sharp vibration. So yes, if you knew that there is that relationship, you were right. But, yes, ladies and gentlemen, there's big buts. And over the next two slides, I'll try to explain what the but is, because that vibration is not necessarily true. All right? Now, please focus for a moment on those dark lines here. It's a cross-section of the rotor. We have pole A on the top, and then pole B at the bottom. You have coil 1 to 6 on one pole. The coils go like this, and then coil 1 to 6 on the other pole. The red lines that you see here, it's the main flux produced by your field. It's the main, well, when I say field, I mean the rotor. If you have an interturn fault on coil 6, as an example here, because of the proximity of coil 6 on the other pole, this fault doesn't have that much influence on the production of the main flux. Now, let's take another example. This time, the fault is on coil 1. Look how far coil 1 on this pole is from this coil 1 on the second pole. Well, basically very far. And what we exaggerated here, just to show you the difference, the gray lines here is the flux from the previous picture when everything was balanced. If you have an interturn fault on one of the short coils, you're going to end up with that magnetic imbalance between two poles. And this will cause a vibration problem. So when you think about it, you can actually conclude. We can say that if the interturn fault is present on one of the short coils, and when I say short coils, I mean the coils that is close to the main pole. So say coils 1 to 3, then most likely, as a consequence of the interturn fault, you will see change in your generator rotor vibration. If, however, you have an interturn fault on the longer coils, so say 3, 4, 5, 6, up to 9, then most likely you won't see any effect on the vibration. And I think thanks to that little picture, you are now fully aware of the difference and the influence of interturn fault on vibration. All right, very good, very well. Let me just have a little break, and we're going to go with two questions. So there's going to be a pool started, and I'm going to ask you two questions. I'm doing it now. If you don't mind answering that question, I would appreciate it. So the first question is, do you often use bearing gear, for example, every day? So in other words, is your machine base load, so running 365 with no stops, or is your machine peak load, so starts and stops every day, maybe even twice a day? I'm going to wait for 10 seconds. 5 more seconds. Okay, and I'm going to show you the results from that poll. So you said that 60% of you have baseload machines. So basically you're in much better conditions than the 42% you see above, because the 42% will have that problem more likely than the baseload machine. All right, thank you very much for that. And there's one more question. Does your generator have vibration problems? Yes. Then yes, under certain conditions. Yes, with random occurrence. And then no. And again, I'm going to give you around 10 seconds. All right. So I'm going to show you the results. So only one person has got problems with the generator. There's no here, and then some of them randomly or under certain conditions have issues. Well, that means for you guys, it should be maybe investigated, because there might be the relationship with the interturn fault. All right, thanks very much for that. Let's get on with the presentation. All right. Now, online methods to detect interturn faults. Why do we want to talk about online methods rather than offline methods? No. So let me read that sentence for you. Interturn faults very often disappear when the generator sits standstill. What do I mean by that? Well, think about it. When you have 3000 RPM and every component is pressing against each other, so say you have two copper pieces and then broken piece of insulation in between. When you have a centrifugal force acting, most likely the copper will touch the adjacent copper. If, however, you stop the machine, that fault can simply disappear. That's why it's crucial for us to understand the online diagnostics rather than offline, because on many occasions when you perform your routine tests when the machine is standstill during annual minor or major overhaul, that simply could be a disappearing interturn fault. So let me go through the online diagnostics. RSO, I guess most of you can recognize RSO, so recurrent surge oscilloscope. It's a very good test, it's a very sensitive method to detect interturn faults, and it's a very simple test as well. So on the left hand side, to give you an example, you have discrepancy between red and blue line. That would mean to the tester that the interturn fault is present in the winding. On the right hand side, you have red and blue overlapping. That means that there's no problems with the winding. It's as simple as that. What else do we know about RSO? Well, sometimes it's too sensitive, as scary as it sounds. Yes, but number of tests we performed in the past, we realized that sometimes RSO can detect non-current carrying short circuits. What it means, let me put it in other words. If you add a short circuit with the 10 ohms resistor, we've noticed that we actually might detect discrepancy between two lines, where 10 ohms resistor isn't conductive. So this is how sensitive RSO is. Something to have in mind when you perform that test. To determine exact location, a drop voltage test is much better option, which again, this will help you to pinpoint exact location. But you can perform something we call reference traces. So what we do every time we have the rotor in our factory and we remove the retaining rings, we will introduce interturn faults artificially, take the reading and save the screen of the oscilloscope. And thanks to that, in the future, when we compare the reading on the machine online with the reading with the reference traces, we can then tell on what coil the fault is. So yes, RSO can be a good tool also to pinpoint the location of the fault. And look how simple it is. So if you have, and it's something to emphasize, guys, it's only dedicated for machines with the slip ring. So if you have brushless excitations, unfortunately, you will be unable to perform RSO tests because all you need is the access to your slip rings. And what you do, you remove the brushes, you just leave one brush per slip ring, attach one of the leads to one brush, the other to the other one. Then on the other side, you connect your RSO kit to the earthing brush, and you simply take the reading. It's that simple. It will take 15, maybe half an hour, and you have your online reading, 3000 RPM, centrifugal force acting. So if you have problems, this will reveal that problem. So it's a good tool. Remember maybe to incorporate that test in your future maintenance activities. Now, flux probe. Well, in my view, this is the best tool available because first, it will reveal only current carrying problems. It's the most sensitive. You can tell where the fault is exactly, and you can also say how many turns in the coil are shorted. So very, very powerful tool. Now have a look at this picture because I would like you to understand what we see. So in here you see the rotor. You have one pole, coil 1 here, 2, 3, and 6, and then second pole here, coils 1 to 6. And the lines here is the main rotor flux. This is the flux that is produced by your fields. And it's not something we're going to talk about. This flux is actually something that we don't like when we take the flux probe reading. And I'm going to tell you why is that. Because what we want to measure is something we call leakage flux. So if you come back to school, you can probably remember that if there's current flowing through the cable, around that cable, you will have magnetic field. And this is exactly what we are interested in. So we want to ignore the influence of the main field, and what we want to measure is that flux that is being produced around each and every coil when the machine is turning. This sensor is installed on your stator and it takes the reading across every coil. And then think about it. If, for instance, this coil has got shorter turns, that leakage flux will be much smaller than the other ones. And then if you compare the signal measured from that coil with shorter turns with the same coil but on the opposite pole, you can then determine and pinpoint the location of the fault. So it's a powerful tool. Now, we need to mention the influence of the main flux that we mentioned in the first slide. So on the left-hand side here, this is the main flux at no low condition. So there's no armature reaction coming from the stator, so the flux is just flowing through the rotor, air gap, and then back through the core. And I would like you to focus on coil 1, where it sits against that axis. It's just right here. Then let's jump in onto the second picture. Here we can see the machine on load. What it means that the flux will be distorted by the load angle. We call that load angle. And have a look that coil 1 here is very close to the axis. Here it's far away from the axis. So what we do, we move the angle of that rotor. And then have a look at this picture now. What you see that the longest coil on both poles has got no influence from that main flux. So you can see the clear spot here. So when you take the reading with your flux probe, you can say that the biggest sensitivity of that reading is here around coils 6 and 5. Then if you change the load angle, what it means you change the power output of your machine, that clear spot moves to coil 3-4, and you continue doing that from power output 0 to your rated power by changing the load angle, so you can have a clear spot and highest sensitivity on each and every coil. I hope it makes sense. It's not easy to understand, but I hope it makes sense now, at least a bit more. So in simple words, when you think about it, that's your capability diagram. And if you want to measure with the highest sensitivity of coil 1, you have to go slightly into the leading power factor. And then coil 5, you go down with the power and you just go through coil 5, 4, 3, 2, and so on. So this is how simple it is, but I want you to remember that the sensitivity of the reading changes with the power. All right? Okay, now we're going to go through one and only one, I can promise that to you, commercial slide. So for those who don't want to listen, please cover your ears, close your eyes, because I will be talking commercial just for one slide. So this slide is showing a PDA, live view PDA product, something that QuartzSelect and QuartzTech is selling. And it's nothing more than the online monitoring system. QuartzSelect and QuartzTech are well known from online partial discharge monitoring systems, but what we don't really mention that often is that we can add shaft voltage module or the rotor flux probe module into the same box. So if you would like to consider installation of that system, please let us know. All right, enough about commercial aspects. Let's continue with the presentation. So another good example, it's actually a very good example because this will mix everything I just said. So if you notice, you have an interturn fault on the bottom coils because you can, if you remember, the retaining ring will be sitting on top here. So we can tell that interturn fault here is far away from the earth potential, so it's not as critical as the one that would be here, for instance. And yet, you have a significant damage going on here with the molten copper. You can see molten copper disappearing copper. That means that the temperature here was more than 1000 degrees. I think 1100 is the melting temperature for the copper. And just to confuse you even more, that was the longest coil. So this operator didn't see a problem with the rotor and rotor's vibration because that was the longest coil, so there was no influence onto the vibration, and yet they ended up with a serious problem and an air fault. So yes, we did say that location is critical, and we did say that it could cause vibration, but that one good example can prove that even with those assumptions, we can have serious problems with our rotors. And the last slide, just a quick summary. Well, we said that interturn faults, if not monitored, can lead to generator failure. And we showed you just a few examples of that happening. Indeed, if you have an interturn fault, it's always good to know where the fault is, so you can perform a proper analysis, technical risk analysis, and then continue with the maintenance regime. We also said that many interturn faults disappear when the unit is at standstill. And yes, this is quite critical in my view because performing your standard diagnostic tests might not reveal the problems with your rotor winding. And with that in mind, I believe as an engineer that it's really worth considering an online test like the RSO we just showed you, or it's worth considering installation of the online monitoring system, because that will continuously monitor the performance of your generator rotor. And I want to leave you with that thought. And yes, there's going to be time for questions and comments. At the end, I would like to go with a few more clues. So if you don't mind answering this question for us, do you use online diagnostic tests already? All right, let me show you the results. So yeah, around 20% of you use, so 80% don't use online diagnostics. All right, thank you very much for sharing that experience with me. And the other one, what online system you have installed? Again, if you don't mind sharing that with us, we would like to learn as much as we can. So partial discharge, rotor flux probe, sharp voltage, or none of the above. I would appreciate your input here. All right. I'm going to show you the results now. So, well, clearly you monitor, well, some of you, 25% monitor sharp voltage, and then nearly 1/5 monitor partial discharge. There is only one operator who said that you monitor rotor flux probes. Not that many. Thank you very much for sharing. And then last question at the end of this presentation before we start Q&A session. Would you like to further discuss generator monitoring system with us? Feel free to say no or yes. It will help us with the follow-up.
Okay, thank you very much. We do have a few questions, Wojciech.
All right.
The first question we have, how often do we need to inspect under the retaining rings, depending on the number of starts and stops?
Ooh, that's a good one. That's a very good one. So we treat, well, every start we treat like between 20 to 30 working hours. So usually your maintenance regime is determined by number of working hours. So when you assume that you remove retaining rings on every major overhaul, number of start and stops will shrink that time or that distance between two major overhauls. Therefore, I would say you should do it more often. But again, treat start and stop as 10 to 30 hours of the running of your machine. That should help you.
Okay, thank you. The next question is, how can we prevent failures in the pole-to-pole connections?
That's a good one. It's a good one. So we know from experience, so you have different OEMs, and again, I don't want to mention them, but different OEMs will have different solutions for pole-to-pole connection. Some of them, which are not flexible, are prone to cracks. So if you have a machine with the old type of pole-to-pole connection, which isn't flexible enough, you might actually end up with a problem. So just to answer a question, we don't know unless we can know what kind of design you have, because some of them are prone to the cracks and then further problems, and some of them are resistant to cracks depending on the flexibility of that connection. But yeah, we can help you to answer that question maybe after the webinar, if we can find out a bit more about your particular machine.
Okay, thank you, Wojciech. We have one more question that's just arrived. Do we have any experience with the cause of circulating currents through the damper, finger and wedges that have produced electrical erosion even in retaining rings?
Oh yes, well, it's a good question. I'm really happy to hear that because over the years we had a chance to work with customers who had machines experiencing these particular problems. We know also that these damages caused by that circulating currents you mentioned can be extremely extensive. And just to give you an example, we had a contract where the OEM condemned the machine. Well, let me put it that way. They said to the customer that you need to buy a new rotor because this one has to be scrapped. And yet, through the big engineering work and study, we managed to recover that rotor within a few months window. And the machine is up and running, and it's been running for the last 4 years, if I remember right. So yeah.
Yes, indeed. And I think this is the final question. Somebody must have looked at your commercial slide. Do we provide customer support as well as the hardware? What kind of customer support might that be?
Okay, yeah, it is an important question. So yes, we support our customers, well, from the moment we have a question if this needs to be installed, and then if something isn't right, our engineers are ready to support you if you have a particular problem on your machine or the online system detects the problem. So always pick up the phone to us, have a chat with us, and if something is really serious going on, we can send an engineer pretty much immediately to give you a hand and help you with the problem.
Right, thank you very much, Wojciech. I think that concludes the questions and concludes the presentation. I would like to thank everybody for attending this afternoon or this morning, depending on your location. We hope that you have learned something useful and enjoyed the presentation. Please feel free to contact myself, Andrea Vona, or Wojciech Betlej, as you see the contact details there. If any questions have not been answered clearly for you, or you wish to talk to us privately, that is of course perfectly fine with us. Any questions related to your electrical machines or anything that you have heard today. So that is the end of the session. Thank you all and goodbye.